Hello, everyone. Can you hear me?
Yes.
Wonderful. We are joining in. Let's wait for a while and then we start. Okay? Okay, 17 of us, not that many. Have you had just now a previous lecture?
I think many forgot about the lecture.
Many forgot about the lecture. Yes.
Our linear algebra laboratory just finished 15 minutes ago.
Finished 10 minutes ago. Okay, so let's wait if you don't mind, because I believe that other people will come in. If not, we'll start maybe in 2 minutes. And then those who are late will nevertheless be able to see the recording of our lecture online, as we usually do. It is not the same as an interactive lecture, but it is still acceptable. So waiting just a little further, and then we start. Okay, let's start. You can see my screen, right? The whiteboard.
Yes.
Yes.
Okay, wonderful. So today is our final lecture on geometry of straight lines and planes. And from next time on, or may even be that we'll have some time left at the end of this lecture, we'll see. We will start second order curves. As you can see from our syllabus on Moodle, second order curves on the plane, in the plane, and later on, second order surfaces in 3D. And then the most exciting part, which will bring everything we have learned so far together, it will be two-body problem and orbital motion in astronomy from the linear algebra point of view. Otherwise, it is not exactly clear why have we started all linear transforms, what are second order curves for. It is all important to see one big application on that. But today it is primarily more about very, I would say, mundane type of objects, which are just straight lines and planes in 3D. You remember last time we discussed the problem of intersection between two planes. So if there is a plane 1 and plane 2 given by, as you now remember, the non-parametric equations a1x plus b1y plus c1z plus d1 equals to 0, and not all coefficients a, b, c are equal to 0, but we don't know which one is non-equal to 0, and for that reason can't divide with that coefficient. So I write it that way. a2x plus b2y plus c2z plus d2 equals to 0. So as we discussed, this means we have two equations and three unknowns x, y, z. Therefore, the system is underdefined and it has not a single pointwise solution, but a set of x, y, z, which are solutions. And this set is precisely, in the generic case, the straight line, which is the line of intersection between two planes. But there are some genericity conditions, as we have seen. So let us, once again, we stopped at this point last time, let us consider the generic and degenerate cases. So first, degenerate cases. You remember we made a matrix, and now let's do it a little bit more in more detail. So first of all, we construct a matrix A1, B1, C1, A2, B2, C2. And together with this, so let me denote this matrix by M. And also let us construct an extended matrix, which is M plus one more column, D1, D2. And also D1, A2, B2, C2, D2, which we will denote, let's say, by P. So what happens? Consider the first degenerate case when you remember we were constructing minors of this matrix, 2 by 2, consisting of the first two columns, the second two columns, or the first and the second. Suppose that the following conditions hold. That the determinant of A1, B1, A2, B2 equals to 0, and the second determinant, which is B1, C1, B2, C2, is also equal to 0. This implies that the third determinant will be 0 as well. Then A1, C1, so that's what we assume. That these two minors have 0 determinants, and then A1, C1, A2, C2, this determinant is also equal to 0. What does it mean? It means that the rows of our matrix A1, B1, C1, A2, B2, C2 are characterized by which property? They are proportional to each other. So we can say that informally, writing as row vectors, A1, B1, C1 is proportional, therefore, with some coefficient k, A2, B2, C2. Or indeed, any of them is 0. Which means that under our definition of a plane, A, B, C coefficients are not 0 together. Therefore, each of them is not a 0 vector by itself, but they're just proportional to each other. So they're also proportional, which means that vectors orthogonal to those planes, first one and second one, are collinear, which means that the planes are, what do I say about the planes in this case?
Parallel.
Planes are parallel. Planes are parallel. Well, maybe. Or it may even be that it is the same plane. Why not? So how do we distinguish between these two cases? Whether planes are parallel or it is the same plane. We consider by the way, I don't remember, we in lectures did not do it, and in tutorials we may or may have not introduced the notion of a rank of a matrix. Did we?
No.
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 No. A rank, actually, we don't need to do it now. The whole concept of the rank will be introduced in very detail in your second term in the linear algebra lectures. But informally, let us see what it means. A rank is for any matrix. By the way, matrix M and matrix P, these matrices are not square ones. This one is 2 by 3, and this one is 2 by 4. A rank is the maximum number of linear independent columns or rows. Let's see exactly what it means. First of all, for non-square matrix, the number it is possible to prove, and you will see this proof in your linear algebra in the next term, the maximum number of linear independent columns or rows is the same. So whether you count it by rows or you count it by columns. Therefore, what it means, we consider a 2 by 3 matrix here. The columns of this matrix are just column vectors of length 2, but there are 3 of them. Whereas the rows of this matrix are row vectors of length 3, but there are 2 of them. So if there are only 2 rows, then the maximum number of linearly independent rows is of course 2. They are either linearly dependent or linearly independent. So if the rows are linearly dependent, then there is only one linearly independent row. By the way, it is also possible in general that there is a 0 number of linearly independent rows. But that only happens if the whole matrix is a 0, 1. then a zero vector, even a single zero vector, is by definition a linearly dependent one, because we can take any non-zero lambda, multiply it by a zero vector, and we get a zero vector for any lambda which is not zero by itself, So a zero vector is by definition a linearly dependent one with itself. But we exclude this because we know that in this case, the rows are not entirely zeros, because these are coefficients of our plane. So at least one of A1, B1, C1 and A2, B2, C2 coefficients must be non-zero. So if there is only one linearly independent row, therefore the second one is dependent on it, like what we put here, they are proportional to each other, then there is only one linearly independent row, and we say the matrix has a rank 1. Because, as we stated, you will see the proof later, the number of linearly independent columns is the same as the number of linearly independent rows, then there is only one linearly independent column. Although there are 3 columns here, but these 3 are linearly dependent, and any 2 of them is also linearly dependent, which means that the column 2 is proportional to column 1, for example. Column 3 is proportional to column 1, provided that that column 1 is non-zero. At least one of them is non-zero, and others are proportional to it, which means that linearly we have linear dependence between rows and columns, so that only one row and only one column is independent of the others. But we can ask a similar question about this extended matrix P, which is now a 2 by 4 matrix. If rows, the first row and the second row in matrix M, are linearly dependent, so there is this proportionality relation between them, then what can we say about the rows of matrix P? It depends. They may be linearly dependent, or they may be linearly independent. These parts are linearly dependent, but now we have D1 and D2. So if D1 and D2 are such that this linear dependency breaks, so for example, we can't say A1, B1, C1 and A2, B2, C2 are connected with some proportionality coefficients, but for example, A1, B1, C1, D1 is not anymore equal to K times A2, B2, C2, D2. Then we say that in this case, a rank of M is equal to 1, but rank of P is equal to what? In a larger matrix P, the rows are not proportional. So in that case, they are not linearly dependent. So what is the rank of P in that case? 2, yes, because there are 2 rows, and these 2 rows are linearly independent. Obviously, there are 4 columns, and of those 4 columns, only 2 of them would be linearly independent. It is the last column, D1, D2, and some other column in our matrix. For example, B1, B2. So if we construct the minor B1, D1, B2, D2, it would have a non-zero determinant. So what does it mean in this case? So you see, the normal vectors which define our orientation of the planes are the same, but the free terms D1 and D2 are not the same. What can we say about this? What is the situation? You remember that, in fact, these coefficients d1 and d2, they depend on the initial points through which our plane is passing, because, in fact, we can write our equation in a similar way. A1 times x minus x0 plus b1 times y minus y0 plus c1 z minus z0 equals to 0. And then our d1 coefficient is just minus a1 x0 minus b1 y0 minus c1 z0. So the initial point x0, y0, z0, it really comes into the free term, into the d coefficient, whereas a1, b1, c1 do not depend on the initial point. So we have two planes with the same normal vectors, collinear normal vectors. But when we take into account the initial points, then the extended vectors a1, b1, c1, d1, and so on, and the same for a2, b2, c2, d2, they are no longer proportional to each other. So what does it mean from the geometric intuition?
Planes are parallel.
Planes are parallel but different from each other. So in this case, yes, where in these situations, planes are parallel but distinct. In this case, our system of equations, which I denote by star, well, what about intersections in that case? There are no intersections. So in this case, really, the system star has no solutions. This is quite clear geometrically, and if you try to solve it by elimination, you will indeed arrive at inconsistent system. So you wouldn't be able to do it. It has no solutions. Okay, so this is the case, if we started with this case 1, degenerate case actually. Degenerate because the rows of M are already proportional to each other. So this case will denote as 1.1, which means no solutions, no intersection line at all. Or we can have case 1.2 when in the extended matrix P, the rows are also proportional to each other. So A1, B1, C1, D1 is equal to a certain factor K times A2, B2, C2, D2. So in this case, a rank of P is equal to what?
1.
1. Rank of P is equal to 1. In this case, what can we say about our planes?
These are the same plane.
It is the same plane. Same plane. And therefore, the intersection is the plane itself. So here there is no intersection line. So the set of intersection points is empty set. Intersection is the plane itself. Which is a 2D, two-dimensional manifold, as we all know. A plane, you remember, is a two-dimensional manifold. Whereas if there is no intersection at all, obviously, this means that it is a 0D manifold, empty set. So these are two degenerate cases. In one case, there is no intersection at all and it is zero-dimensional. In the other case, the intersection is a plane itself, which is two-dimensional. Okay? Now, we consider the generic case. 2 is the generic case. In the generic case, the rank of our matrix M, which is 2 by 3, is equal to 2. So rows of M are linearly independent. Then we can really take, as we actually described in the last lecture, for example, take one coordinate as a parameter, solve the system. It depends on which minor is actually non-degenerate one, and we obtain the intersection as a straight line. So intersection is straight line. One D. But perhaps there is an easier way than just solving, finding out which minor is non-degenerate, non-singular, has non-zero determinant, and then solving system and introducing parameterization. Perhaps there is an easier way of how we can solve this system. And indeed it is so. We will do it with the help of a vector product, cross product. You see that if we have two planes, it is pretty much obvious. So suppose that there are two planes intersecting each other. Excuse my hand drawing. And there is an intersection line between these two planes. And then, obviously, this intersection line belongs to both planes. And then if we have normal vectors on these two planes, then because this intersection line belongs to both of them, then it is orthogonal to both of them. If it is orthogonal to both of them, then a vector which is collinear with this straight line would be orthogonal to both normal vectors. And if it is orthogonal, then it can be viewed as a vector product between the two. So basically, if we have, for example, this vector is, for example, this vector is, let's say, A2, B2, C2, and this one is A1, B1, C1, and we construct the vector product A3, B3, C3, which is a cross product of A1, B1, C1 times A2, B2, C2, then indeed this vector product must be pointing towards, must be pointing along the intersecting line. Only my question is, in this particular case, to the left or to the right in my hand drawing? This vector would be pointing along this line to the right or to the
To
left?
the left. To the left.
You remember the rule is, it is pointing, the vector product is pointing in such a direction that if we look from the end of this vector, then the shortest term from the first to the second one must be counterclockwise. So that's the first one, you remember that's the first one, and that's the second one. So if you look carefully enough, for example, I move the first one parallel to the same beginning as the second one. Therefore, that's the shortest term from the first to the second, and it goes, if we look at it that way, yes, it is clockwise if we look and as we do from that end. Therefore, not like this, and you're absolutely right, it is pointing to the left in this case. That's correct. So, and we already have the directing vector of our intersection line. Obviously, this is not enough to specify our line, and we still need to find some single point x0, y0, z0, which belongs to both of them. And then how do we find it? Unfortunately, it still means that we need to solve our system of linear equations. But it is an easier task in this case, because we already know that under those genericity conditions, the system is solvable. And secondly, we don't even need to find a general solution to it. It is sufficient to find just a single point. So basically, we can do what? We can, for example, take any arbitrary value of z, provided that a1, b1, a2, b2 minor is non-degenerate, and then with that given value of z, solve for x and y, and we get that single point of intersection. Once we got, by solving a linear system, a single intersection point, then we can provide the general equation for the whole line, as obviously for the intersection line it would be x, y, z equals to x0, y0, z0 from the system of equations. Actually, it is system star, any solution to system star, plus t, where t is a real parameter, a3, b3, c3. So it is pretty easy to find the direction of our intersection line. It is slightly more involved to find any single point it passes through, because it still requires solving a linear system, but in that case, the system would be a very simplistic 2x2 one. And obviously, this vector a3, b3, c3 is not 0 if and only if we are in the generic case. The genericity condition holds. And this genericity condition is precisely that rank of M equals to 2. The rows are linearly independent. If the rows become linearly dependent, then, although non-zero, then the vector product immediately becomes 0. Okay? So that should be pretty clear.
I have one more question. So we find a precise solution by basically brute force.
Well, solving a 2x2 system is not that much a brute force.
I mean, initially we have to take some arbitrary value of z to solve 2x2.
We need to find. Let us dwell on that little bit more. So it is a good point. So yeah, basically you are right that we do have already A3, B3, C3, but we need to find this x0, y0, z0, at least one point. So let us examine our system of equations once again. So in order to find this point, we again consider the same system star, but I now write x0, y0, z0 for that case, for that. So a1 x0 plus b1 y0 plus c1 z0 plus d1 equals to 0, and same a2 x0 plus b2 y0 plus c2 z0 plus d2 equals to 0. So how do we do it? We consider 3 minors of size 2 by 2 in our system. The first one is A1, B1, A2, B2. The second one is B1, C1, B2, C2. And the third one is obviously A1, C1, A2, C2. At least one of them, because we're in the generic case, so a rank of M equals to 2. This is equivalent to the fact, let me denote this this by M MAB, MBC, MAC. Then at least one of those minors, MAB, MBC, MAC, is non-degenerate. Non-degenerate means has a non-zero determinant. At least one. It may be that 2 of them or even all 3 of them are non-degenerate, but at least one of them is non-degenerate. Suppose that determinant of MAB is not 0. So this one is non-degenerate. Okay. Then we do the following. Take any z0 a real number and consider a linear system a1 x0 plus b1 y0 equals to minus d1 minus c1 0. A2 x0 plus b2 y0 equals to minus d2 minus c2 z0. Because this system is non-degenerate, then it has a unique solution. Unique solution x0, y0. And then x0, y0, and z0, which we just postulated, anyone. For example, just to make things easier for you, you can say you take Z0 equal to 0. This is fine. It's the initial point. Similarly, if, for example, this minor is not applicable, but this one has a non-zero determinant. Excuse me, I made this line. It doesn't mean that I crossed it as an incorrect one. It's just my system drew it. Okay, everything we wrote is perfectly valid. Then what? Then you solve it for y and z. So you take any value of x. For example, you may take x0 equal to 0, and then you solve the system with respect to y0 and z0. Or if this one is not applicable, then you may consider the first and the third one, A1, C1, A2, C2. But at least one of them must be non-zero. Okay?
Yes, now it's perfectly clear. Thank you.
Yes. Oh, by the way, if both MAB and MBC are degenerate, then the third one will be degenerate as well, and you don't even need to try it. Okay? So we know that at least one of them is non-degenerate. So take any non-degenerate one. And then we know that actually two of them must be non-degenerate, because if two of them are degenerate, then all three of them are degenerate. So that's all about how we solve it. Now, I would like to consider two problems which are very important, actually, both geometrically and from applications, and you will find them geometrically beautiful, I would say. Problem 1. Maybe you have already seen it in the tutorial today, but it is important and it is worth mentioning again. Suppose that there are two vectors, A and B, and we say these are, let's say, our some kind of basic vectors. This is a basis. They are not collinear to each other. So A is not collinear to B, which, as we know, mean that the vector product of A times B is not equal to 0, which means that A and B define a plane, right? As we have seen in the previous lecture. And there is another vector, C, which in general does not belong to this plane. What we want to do is to decompose our vector C into its projection onto plane AB. So we see that's the projection, and this is the orthogonal complement. So the projection will be called C projection, C parallel, although it is not parallel. Well, yes, C projection, and the orthogonal component will be called C orthogonal. So obviously, vector C needs to be decomposed into a sum of two vectors, C in plane plus C orthogonal, where if C, which is in plane, then it is a linear combination of A and B. So it is A alpha plus alpha A plus beta B. So it belongs to the plane AB. And C orthogonal is really orthogonal to A, and C orthogonal is orthogonal to B. Is orthogonal to plane AB. As we know, for that it is sufficient for a vector necessarily insufficient to be orthogonal to two vectors in this plane, so both A and B. Okay? How do we do this decomposition? So we want to decompose C into this. This is a projection on the plane, projection of C onto the plane. And this is the orthogonal, let's say orthogonal complement. What should we do? Any ideas how would we solve this problem?
You can use cross product of A and B, which are orthogonal to the plane AB.
Yes. So yes, let us consider, we will compute the vector I denoted by n, which is the cross product of A and B. Okay. Obviously, yes, when we do this type of decomposition, then this orthogonal complement is not unique. So if instead of product A and B, we consider B by A, we would look into the normal vector going into the opposite direction, and the projection of our CSC orthogonal would change sign in that case. But up to sign, it will be uniquely defined. So suppose this, we constructed a normal vector A cross product B. Then we know that our C orthogonal is actually collinear to this vector n. All right? So what we can do? So n is this vector, for example. Okay? So, which means if it is collinear with n, we can write C orthogonal as just some coefficient which we don't know yet. Let's say some coefficient gamma times n. So it's gamma times AB, where gamma is some real number. Okay. How would we determine this gamma? Okay. Let us go back to our original equation. So we say C, the original C, equals to our C in plane plus C orthogonal. And this C orthogonal is gamma n. And this is a C in plane, which is not yet known. Okay? Now, multiply this equation using a dot product by which vector? By n. Multiply it by n. Then we say a dot product C times n equals to C parallel dot product n plus gamma n times n, which is the absolute value of n squared. All right? But what is C in plane dot product n? What about this term?
0.
0. You are right. They are orthogonal to each other. due to orthogonality. And from this, we immediately get gamma, and obviously the absolute value of n is not 0, because the vector product we know is not 0. N is just a vector product. Therefore, gamma is c times n divided by, I can say n times n, where n is just a times b. And therefore, we immediately got our C orthogonal equal to gamma n, and therefore it is C times C dot product n divided by n dot product n. Both the numerator and denominator are just numbers, and now multiplied by the vector n. Okay? So we now got the orthogonal projection. I mean, the orthogonal component, the orthogonal complement. And it remains to find out the C parallel. How do we construct the C parallel in this case? The C which is in plane, projection to the plane itself.
It's like difference between C and C orthogonal.
Of course, simply take the difference. That's our equation 2 star. From the equation 2 star, we simply say it is C minus C orthogonal. So first we compute the C orthogonal, and then we compute the parallel. So basically the problem is solved. And please remember, understand and remember this procedure, or maybe even remember the formulas, because this is what really likely to, first of all, to be useful and used in a great number of applications. And secondly, it may be a problem in your midterm and in the final exam. One final thing which I probably want to do is to construct the decomposition for C parallel with respect to the original A and B. Because C parallel, we know that it belongs to the plane AB. Therefore, C parallel, after we found it, is alpha times A plus beta times B. Can you propose any ideas of how to construct A and B, alpha and beta coefficients? What can we do? So the question is, how to find alpha and beta? Well, there are two ways. The first way is expand this in coordinates. So we have three coordinates of each vector, so x, y, z, and one equation here. All right, an equation in coordinates. So for example, it will be cx, cy, cz equals to alpha times ax, bx, cx plus beta times bx, sorry, what do I do? A, y, az, bx, by, bz. Ay, az. The unknowns are alpha and beta. You can view it as a system of linear equations with respect to alpha and beta. So we have three equations, two unknowns, which mean that the system is over-defined, but we know that it is not over-defined because we do already know, sorry, this is for C parallel, so not for C itself, for C parallel. We know that it is not over-defined because C parallel does indeed belong to the plane AB, so it has a solution. But by construction of C parallel, we know that this system has a solution. Well, we can do it that way, but it is probably not the best way. I would say little bit tedious. So I don't recommend it. Any better way? Any better way of how we can solve it? Remember, we are solving this. C parallel A and B are known. So when we write it in coordinates, we get a system of three equations and two unknowns, but we do know that the system is consistent. We have to solve it. Okay, any better way? Let's make scalar products, dot products. But remember that A and B are not necessarily orthogonal to each other. And therefore, we would not have very easy, almost all zero coefficients when we construct dot product. So we multiply this equation by A and by B. So we get A times C parallel. We already know C parallel, so this is well defined, equals to A times A alpha times AA plus beta times AB. In a similar way, B times C parallel equals to alpha times same AB plus beta times BB. Or in a matrix form, we make a matrix 2 by 2, A times A times B, A times B again, and B times B, times alpha beta equals to our right-hand sides. A times C parallel and B times C parallel. Okay. So what about this matrix? Let me denote it by, for example, Q. The determinant of Q equals to A squared, where for A squared, I just use a shorthand notation. A squared is A times A equals to the absolute value of A squared. It is just a shorthand. A squared B squared minus AB squared. And this determinant is not just not equal to 0, but we can say that this determinant is actually strictly positive. You will see why. Because A times B, dot product of A and B, is equal to AB, the product of absolute values, cosine the angle between A and B. Because we know that the vectors A and B are not collinear, therefore this cosine is not equal to plus minus 1, right? If the angle is 0 between them, then it would be 1. If the angle is pi, so they are opposite to each other, then it would be minus 1. But it is neither. They are not collinear. So this cosine is not equal to plus minus 1. And therefore, the absolute value of AB is less than A times B, because it is multiplied by the cosine, which is less than 1. So the absolute value of the cosine is less than 1. And because the absolute value of the cosine is less than 1, then from this it follows immediately, you can already see that A B squared is less than A squared B squared, and therefore, so the second term is strictly less than the first one, and therefore the determinant of Q is greater than 0 indeed. So this matrix Q is symmetrical and with a positive determinant. Later on, when you study the theory of matrices in your next term, we will call such a matrix a positive definite one. So you will see what it exactly means. For the moment, just remember the term. Positive definite matrix. From which you can see immediately that the system is solvable, so you can really solve it, and you determine alpha and beta. So your vector alpha beta exists and is unique. So that's it. Now basically what we did. First, we constructed the vector product. From the vector product, we constructed the orthogonal component, C orthogonal. Then we constructed the C parallel as the difference from between C and C orthogonal. And then we decomposed this C parallel with respect to A and B using this scalar product trick and proving that the corresponding matrix Q is positive definite, and in particular it has a non-zero determinant. So we could determine the coefficients A and beta, alpha and beta. So our first problem is completely solved. Okay? Any questions on that? No? Would you like a short break, really 5 minutes, so we proceed to the second problem? That will be the last one for today. Let's make a very short break.
Maybe it is a good idea.
Yes,
Yes,
short
maybe.
break. Okay, 5 minutes and then a second problem. Okay, back to our lecture. In the remaining half an hour, we'll consider the second geometrical problem concerning now only straight lines. Suppose that there are two generic straight lines in the space. Unlike straight lines in a plane, the straight lines in the space in the generic case do not intersect. And indeed, we assume that these lines do not intersect. Non-intersecting straight lines in 3D. But we know from the school geometry, and we'll see now in more detail how it happens, that we can define such a thing as the distance between these straight lines. More precisely, so suppose that these are two lines. So for example, this is L1, line 1, and this is line 2. There is a certain point in the first line, let's denote it A by A, and a certain point in the second line, which we denote by B, such that the straight line segment AB is orthogonal to both, actually, the first and the second one. You can think of, in this case, lines L1 and L2 lying in two parallel planes. So this would be, for example, a plane of the first one. This would be the plane of the second one, and AB being the distance between these two parallel planes. So our problem is the following. Suppose that our lines are given by their equations. For simplicity, we would say given by parametric equations. So L1 is given by xyz equals to some initial point, which I denote by x, let's say 0, 1, y 0, 1, z 0, 1, plus t, directing vector, let's say a1, b1, c1. And L2 has equation xyz equals to some completely different initial point. By the way, this is not A and this is not B, just some initial points which may be 1 million light years away from us. We don't know. They're just some given points. x02, y02, z02 plus t a2, and actually the parameters are even different. So let's determine, let's denote them by different letters. So for example, this is a parameter t1, this is a parameter t2. A2, B2, C2. T1, T2 are real parameters. Again, we can assume that the directing vectors are obviously non-zero. And we need to find A and B such that A belongs to L1, B belongs to L2. The vector AB is orthogonal to L1 vector AB is orthogonal to L2. Okay, so that's what we want to do. How do we do it? You already probably have an idea what to do. If vector AB is orthogonal to both L1 and L2, and L1 and L2 have directing vectors given here, A1, B1, C1, A2, B2, C2, then we can construct this vector AB. Well, some vector collinear with AB. Let me denote it by, let's say, some vector D. I can construct vector D. It is not AB itself. It is a vector which is collinear with AB. But in that case, I can construct vector D as a cross product of A1, B1, C1 and A2, B2, C2. Let me denote this vector D just by convention as A3, B3, C3. So once again, that's D. And you remember from the vector product, the cross product formulas. So tell me please, so what would be the first component? What is A3? How do we express it?
It will be determinant of
B1,
B1.
B2, C1, C2.
Yeah.
So it is B1, C2 minus, let's say, C1, B2, that way. Then the second component, it is a determinant of what?
A1, A2, C1, C2.
Almost, with a minus sign.
Yeah.
That's important to remember. With a minus sign. So it is other way around. C1, A2 minus A1, C2. And the final one is, of course, the first determinant, A1, B2 minus B1, C2. When you write this, always check the columns, that each column contains a permutation of our symbols, in this case, B, C, and A. So the first column, by the way, contains indices only 1, 1, 1, 1. The second one, 2, 2, 2. Then again, 1, 1, 1, and 2, 2, 2. And a permutation, B, C, A, C, A, B, C, A, B, B, C, by the way, A. Okay, now that's correct. If we got confused about the sign here, then instead of a permutation, we would have repeated symbols in the corresponding column. And that's no good. Okay, so we constructed our vector D. What else? In that case, our line AB can also be given by a certain equation. So similar to L1 and L2, our AB can be given by equation also x, y, z would be equal to what? We can say what is the initial point. So for x 0, 1, y 0, 1, and so on, these are some remote initial point. For example, this is initial point 01. This is the remote initial point 02 somewhere. But for AB, the initial point is really, let's say, A. So for AB, the initial point is A, XA, YA, ZA plus some parameter which I denote by T3 in this case, times the directing vector, and in this case, the directing vector is precisely our vector D, A3, B3, C3. Okay. So, but what is XA, YA, ZA? On the other hand, A belongs to L1, and therefore for XA, YA, ZA, from the L1 equation, we can write XA, YA, ZA equals to X01, Y01, Z01 plus T1 times A1, B1, C1. Okay? Furthermore, B belongs to L2. And therefore we can say X, well, B belongs to L2, and we can say XB, YB, ZB equals to X02, Y02, Z02 plus some T2, A2, B2, C2. But on the other hand, B belongs to AB. And for AB, we already got this type of equation. Therefore, we can say that XB, YB, ZB equals to this XA, YA, ZA plus T3 times A3, B3, C3. So we now construct the equations taking XB, YB, ZB from those equations and XA, YA, ZA from those equations. We finally get, okay, in the left hand side it will be X02, Y02, Z02, that's for B point, plus T2 times A2, B2, C2 equals to, in the right hand side for XA we take this, X01, Y01, Z01 plus T1, A1, B1, C1, and don't forget plus from this equation T3 times A3, B3, C3. The unknowns here are obviously T1, T2, and T3. These are the unknowns. We can write this in a matrix form. So consider this matrix A1, B1, C1, A2, B2, B2, C2, A3, B3, C3. Okay, A1 is multiplied by, the first column is multiplied by T1, the second by, if we move everything into the right-hand side, by minus T2, and the third one is by T3. So if we put it that way, you see that it is correct. T1 minus T2 and T3. And then indeed, you get equations A1 T1 minus A2 T2 plus A3 T3 equals to, for example, x02 minus x01, and so on. So check that these are actually equivalent notations. X02 minus y, x01, y02 minus y01, z02 minus y02. Okay, so then in order to get T1 minus T2 and T3, it is just sufficient to solve this system. So what can we say about this matrix? So can we solve it? Is this system solvable? Remember that A3, B3, C3 are not independent of A1, A2, and so on, because actually A3, B3, C3 is a cross product of the first two columns. It is A1, B1, C1 cross product A2, B2, C2. So let us denote this matrix by, for example, S. Sorry, I'm pressing the wrong button, S. Then, as a very simple algebraic exercise, if the third column is given by a cross product of the first two, you can very easily see, just let's say algebraically, that the determinant of S is a very, very, very simple one. It is just the length of the third column. It is going to be A3 squared, verified by direct computation, plus B3 squared, plus C3 squared, which is obviously not 0, well, greater than 0, because A1, B1, C1, and A2, B2, C2 are not collinear. Well, or maybe they are collinear. If they are collinear, then it is a degenerate case. Or if collinear, degenerate case. So let's say not as, but if. Degenerate case. Consider the generic case first. Consider the generic case first. Generic case. Determinant of C of S is positive. Then we get unique T1 minus T2, T3, and you get A and B from T1 and T2. Okay. If they are collinear and the determinant of this system is 0, it means that the lines are parallel to each other, and there is no unique vector d connecting the points. Well, the vector d in this case is if you have two collinear lines. How do we construct in this case? What do we need to do? The points A and B are no longer uniquely defined, obviously, because you can take AB here, you can take AB in any other place. Degenerate case. So we can't determine A and B uniquely. What we can determine the distance between the lines. So in this case, once we got AB, then obviously the length of AB is the distance. In the degenerate case, by the way, there are again two degenerate cases. Degenerate case 1, parallel but distinct lines. D2, same line. Okay. How can we distinguish between those cases? Whether it is parallel but different, or it is the same line. In both cases, because the directing vectors of these lines are collinear, we say that if we construct the matrix, for example, A1, B1, C1, A2, B2, C2, the rank of this matrix is equal to what?
1.
Is equal to 1. Okay. Now, what can we say? What can we say about whether, in this case, the lines are really the same, or the lines are parallel but distinct from each other? We need to take into account the initial points. We take into account the points x 01, x 02, sorry, y 01, z 01, and x 02, y 02, z 02. So that the initial point. So let's suppose that this is our L1, this is our L2, this is the initial point O1, this is somewhere the initial point O2. Okay, what can we do? Let us construct a vector which connects those 2 points between O1 and O2, all right? By the way, this is the vector here in our right-hand side. That's the vector. This is the vector O1, O2. So, construct the vector O1, O2, which is equal to, in coordinates, x02 minus x01, y02 minus y01, z02 minus z01. And now construct the extended matrix. The extended matrix A1, B1, C1, A2, B2, C2, and this vector O1, O2, x02 minus x01, y02 minus y01, z02 minus z01, which I denote by U. Now rank U may be equal to not 1 anymore. It would not be equal to 3, because we already know that since the rank of the original matrix is 1, therefore the columns, the first and the second one, are linearly dependent. Because these columns are linearly dependent, then the matrix U cannot have 3 independent columns. Therefore, it may only have either 1 or 2 independent columns. So it may be still 1 or 2, but not 3. If the rank of this matrix is still 1, it means that the third column, and remember the third column is our vector O1, O2, is again collinear with the first directing vector and the second directing vector, which means that it is same line. And if it became 2, then these are distinct parallel lines. Well, if it is same line, then obviously distance is 0. If these are distinct parallel lines, so we do know indeed that they are distinct, then I would, what would you do? How would you compute the distance between them in that case? I will leave it as a small exercise for you. We already know that they are parallel. We know they are distinct. Compute just the distance between them. Exercise.
Excuse me, when we say the same line, does it mean coincide or really the same?
You see, these are not vectors. When we say same line, it really means same line as a geometrical object.
Okay,
So same line. Well, if two geometrical objects being straight lines coincide, then it is same line, yes, or two coinciding lines, but in fact there is only one.
Okay.
And in that case, the distance between them is 0. If these are two distinct parallel lines, then we know that the vector O1, O2 does not belong to, is not collinear with the same, with directing vectors of L1 and L2. So we know that these points do not belong to the same line. Then there is a relatively easy way of how we can compute the distance between them. Well, as a hint for you, what you can do, because the directing vector of each line is known, then suppose this is the directing vector, you project this vector O1, O2 onto the directing vector in a similar way as we did it for projecting to a plane. Then you take the difference. The difference would be orthogonal to both lines, and the absolute value of that difference is the distance between lines. So finish it and get formulas. It is useful because you may get that type of problem, for example, in the midterm, but that's not difficult. If any questions, please write to me in Telegram. I will be happy to answer. That's all. We're just in time.
Thank you.
Thank you. If
Thank you.
any questions?
No.
No.
So,
Okay.
Bye.
So we are done with straight lines and planes, and it remains for you to pass a midterm next week, which will be in your tutorial and lab time. We will do probably something like, I think, 2 hours for the midterm, 6 problems. And in the lecture next week, we'll start with second order curves or conics or conical sections, ellipses, parabolas, hyperbolas, and like. Thank you.
Thank you.
Thank you. Goodbye.
Goodbye. Thank you.
Thank
Bye.
you. Bye.